First of all, I'm very loud. First of all, I want to thank the organizers for an excuse to come to Croatia for my first time. I'm really enjoying it, and I'm enjoying the conference. I'll be talking about phase reduction. This is very much in the spirit of Horoya's talk on the first day. Um, and what's the point? Why am I presenting this to you? My hope is that maybe the Koopman world, which I'm only tangentially part of, will find some of these ideas to be interesting and maybe applicable to what you're doing. And certainly, I've been taking a lot of notes during the Koopman world's talks and trying to think how they can be applied to the way I think about these things. So, the sorts of problems I'm interested in are things like this. Okay, this is a model for a heart pacemaker cell. And the reason we were interested in this is we were interested in controlling a cardiac arrhythmia. So trying to prevent, some heart issue. Here it's for a rabbit, but, similar models would apply for humans. And this is a mess, right? This is a very complicated system. It turns out there's only two ODEs, but you see there's all these functions and all kinds of constants. And, in mathematical biology, the models are a huge mess. Okay. And we want to simplify these models in some way in order to make some progress. And so we use phase reduction. Okay. And we've heard a little bit about isochrons. Oops. This is something everyone does, right? Okay. Oh, now I've lost it. Okay. So, um, Isochrons are defined as follows. So if I have a dynamical system, dx dt equals f of x with a stable hyperbolic periodic orbit, isochron is a set of initial conditions share the same asymptotic convergence to a periodic orbit. You can think of them as a level set of a phase variable, theta. And what's nice about these is you get a very simple equation, d theta dt is equal to a constant. Okay. And here's the little animation I made a while back about isochrons. The black curve is a stable periodic orbit here. The blue lines are isochrons that are equally spaced in phase. What I'm trying to illustrate here, start with three initial conditions on the same isochron. Well, it's a stable periodic orbit. The trajectories all approach the periodic orbit, and they approach in phase with each other. So all three of these actually fire at exactly the same time because they start on the same isochron. Okay. A little bit of history of isochrons. So Art Winfrey, to my knowledge, is the first person to use this term back in 1967. This is kind of a footnote in the paper where he uses the word isochron. Some other notable references, John Guggenheimer, kind of put them on a firmer, rigorous standing. Kuramoto certainly did kind of in parallel some very interesting work. Art Winfrey, the first edition came out in 1980. Second edition in 2001, wrote this book, Geometry of Biological Time. Now, why am I talking about isochrons? Well, they're related to Koopman, as I think a lot of you know. Here's just my little way I understand it. So, d theta dt equals omega, so you can solve for theta as a function of time. We let this function alpha be e to the I theta of x, and then I apply Koopman to that initial condition. And if I work through, I see that I get exactly the alpha times x0 times e to the I omega t. So, alpha is an eigenfunction of the Koopman operator. Okay. A little history of computing isochrons. I didn't show, in the olden days, you just used various kind of backward integration methods and stuff like that. Back in 2010 with Hinka Osinga, we formulated this as a two-point boundary value problem related to spectral properties of the Koopman operator. So Alex and Igor, and then I got involved with one of the papers there. With my colleague Frederic Jabou, we then did a Hamilton-Jacobi formulation of this and so on. And isochrons are quite beautiful. I don't know to what extent people have looked into these, but this was with Hinka. Oops, sorry. With Hinka, we were able to essentially follow isochrons to, there's an unstable periodic, or sorry, unstable fixed point here. These extra lines are just the so-called null lines of the system. They intersect at the fixed point here, and they spiral in to this unstable fixed point in a very nice way. And if I pick out a single isochron, this is what it looks like. And I tried to freehand because it's hard to see what's going on, not terribly artistic. But if you follow the isochron, you see it kind of goes around in this nice way. It doesn't intersect itself anywhere, approaching a fixed point somewhere. Okay. So isochrons are cool. I like isochrons. Okay. Now, I'm also interested in control. So let's say we have our dynamical system, dx dt equals f of x. It could be that nasty set of equations I showed at the beginning, and I perturb it somehow. So I add some epsilon times g, could be a state-dependent perturbation, could depend on time. If I just explicitly say, okay, what's d theta dt? Okay, that's the gradient of theta dot dx dt. I know what dx dt is, so I plug that in. I can simplify, okay, gradient of theta dot f. Okay, some of you who, uh, you know, think about the theory of would immediately recognize that as omega. Another way to think of it is if I just set epsilon equals 0, this term goes away, and I know by definition d theta t must be equal to omega. But then I have this extra term. So I have the gradient of theta dotted into the control input. Okay, this is all exact up to this point, but typically in the business, in the math biology world, we'd say, okay, well, let's consider weak perturbations. And so we evaluate this on the limit cycle for the unperturbed system. Okay, when I do that, we call this function z the gradient evaluated on that periodic orbit. And simplifying even further, typically in the applications we're interested in, you would have an electrode which supplies an electrical current to your system, and that only affects the voltage equation. Okay, so that's in the first component of my x variable here. So I just have some function u of t, and then I get this very nice equation, d theta dt equals omega, plus this function z sub v is just the voltage component of this function z multiplying u. Okay. Now, it turns out I personally have gotten a lot of mileage out of studying this equation. And I'll show you, actually not all of it. Well, okay, before I do that, maybe a little more about z. So in the math biology world, we call this a phase response curve. And it captures the effect of impulsive perturbations in the voltage. What I find very interesting about this is timing is everything. So you can do the exact same stimulation. Let's say you do a little delta function of current. If I do it here, okay, it's going to make the phase less than it was had I not stimulated it. So it takes longer to, if it's a neuron, longer for the neuron to fire its next spike. But if I do the same exact stimulus at this phase, it advances the phase and makes the neuron fire quicker than it would have had I not stimulated it. So the same exact stimulus, depending on the timing at which I apply it, has a different effect. Turns out it can be measured experimentally. Not easily, okay? People back in the day, their whole dissertation was experimentally a measure phase response curve, but that's kind of cool. Okay, this is actually something you can measure for a system. Here I'm showing it for the so-called Hodgkin-Huxley equations, which is I view as like the hydrogen atom of mathematical neuroscience. Okay, well, it can also be found by solving an adjoint equation. Okay, so here my notation is this is the gradient of theta evaluated on the periodic orbit. Okay, so you have this, F was the original vector field. So from the original vector field, you can form this equation. Here's a normalization condition. And you can solve it analytically in certain cases if you assume you're close to a bifurcation, at least in an approximate sense. You can get a sense of what it looks like. Or, okay, Bard Ehrmantraut wrote a package called XPP, and it's built in the package to solve this adjoint equation. Okay. So as I say, I've gotten a lot of mileage out of this equation over the years. So for example, maybe you're interested in optimal timing control. So let's say my neuron is firing periodically in time, and I want it to fire at a different time. Okay. How can I do that? And what does optimal mean in this sense? Usually what we mean is we want to minimize the energy that you're putting into the neuron. So it would be like an integral of u squared. Okay. Turns out, in a certain limit, the optimal control is essentially just the phase response curve itself, which is kind of cool. Um, and I would say, like, in the control world, if I gave them this problem, say Hodgkin-Huxley equation, system of four coupled nonlinear ODEs, they could probably solve the optimal timing control problem directly from those ODEs. It'd be computationally a bit of a mess. And then they would get an answer, but they'd have no idea why it looks the way it does. Whereas by doing the phase reduction first, we can say, oh, it has to do with the phase response curve. Another problem is maybe want the neuron to fire as quickly or as slowly as possible, given some constraint on the input. Again, the optimal input can be understood in terms of the phase response curve, or what we called optimal chaotic desynchronization. And I'll say a little more about that because we proposed it as a way to treat Parkinson's disease using deep brain stimulation. So in deep brain stimulation, they implant an electrode into a patient's brain. They inject an electrical signal into the brain tissue. If you choose the right signal, it can make the symptoms go away. That's a whole other talk I could give, but it's not terribly Koopman related, so we'll save that for another place. But what do you want to do? It turns out for Parkinson's patients, the belief is the neurons are synchronized when you don't want them to be synchronized. And so you want to design a control input which desynchronizes the neural behavior. And it turns out, in, again, a certain limit, the optimal input is just related to the derivative of the phase response curve. Okay. I will return a little bit later in the talk to this optimal timing control problem. But here for optimal chaotic desynchronization, just to give you a flavor for how these calculations go. So we have our phase model, theta I. So here I'm starting with just two neurons. So theta I is the phase of the ith neuron. These are identical neurons. They have the same frequency. They have the same phase response curve. And crucially, they get the same input. So in deep brain stimulation, there's a single electrical probe that's put into the brain. It's not like every neuron you have the ability to affect independently. And that's part of the challenge. You have one input and you're trying to control the behavior of 1 million neurons or something like that. Okay. We let phi be the phase difference between the neurons. If you work out what d phi dt is, you get this. If I drop this term, I get phi goes as e to the capital lambda times t. Capital lambda here you can think of as a finite time Lyapunov exponent. And it's just this integral in terms of the derivative of the phase response curve multiplying the input. And so our idea was, let's design an input which maximizes this Lyapunov exponent. So if you know chaos theory, positive Lyapunov exponent means exponential divergence of trajectories. Well, that would correspond to desynchronization. So if the neurons have different phases from each other, they're not synchronized with each other. Okay, so putting it as an optimal control problem, now I want to minimize the amount of energy that I input to make this happen. And then the c prime times u, that's basically the Lyapunov exponent. We put a constant beta in here to just kind of weight the importance of the two terms. I put a minus sign because I want to minimize this. So if I minimize negative z prime times u, that corresponds to maximizing positive z prime times u. This is a Lagrange multiplier just to ensure the dynamics get satisfied. When you turn calculus of variations crank, you get a 2-point boundary value problem. And then once you solve this, subject to the appropriate boundary conditions, you get the optimal input here. And the way we used this was we said, okay, so this is derived for 2 neurons, but really we want to control a population of neurons. So what we do is we say, well, let's track the average voltage of the population. If the neurons are all in phase with each other, you get kind of a spike corresponding to the average voltage. And if you exceed that, some threshold for that, you apply this input, okay? And if things become desynchronized enough, then you don't need any more inputs. Okay, so here, just to give an idea, here I have no control. There's 100 neurons. They're noisy. Each neuron feels a different realization of noise, and they're coupled. And you can think of it as the coupling is trying to synchronize them. The noise is trying to desynchronize them, or it has a desynchronizing influence. Okay, so if I plot voltage versus time, for that case, each of these black lines corresponds to a different neuron. The red line is the average voltage, and you see that they're going above threshold. So this would be a situation, very idealized, but this would be a situation where the Parkinson's patient is having the symptoms. Okay. Now, when we do the control, as I described, using this optimal chaotic desynchronization, this is what we get. When the dots are red, that means that the control is on. When they're blue, the control is off. So when the dots are red, the control is trying to exponentially desynchronize the phases of the neurons. Eventually, sorry, I feel like I lost this. No, need any more inputs. But then remember, coupling tends to resynchronize the neurons. So when it resynchronizes them, then you might need more control inputs. So when you look here, we actually had an on threshold and an off threshold. But basically, the neurons are too synchronized here. So we have the inputs. Eventually, we fall below threshold, no input needed, but then the coupling resynchronizes. So we need another series of inputs here. And then here's a long stretch where you don't need any inputs. And this is good from an energetic standpoint. I didn't mention this, but deep brain stimulation is operated by a battery implanted in the patient. And if the battery runs out, they have to have surgery to get a new battery implanted. And, so if we can use the least amount of energy possible, that's good. It makes the battery last longer. And so not only have we optimized energy in order to get this desynchronizing influence, but also we're able to turn it off for quite a while. And we kind of ballparked a little bit compared with the way they currently do deep brain stimulation. This needs about 1,000 times less energy. Okay. Ignoring some of the kind of sensing that would be necessary for this. But at any rate, we were quite happy about that. Okay, just a recent extension under review right now. We're revisiting this problem, but putting in amplitude constraints. So if you know optimal control theory and so on, there's all kinds of cool problems like this that you can play around with. Okay, but let me remind you, I started with how do we control the model? And for this particular model, what we were actually interested in is, it's a pacemaker cell, but similar to a neuron, it's like it's going to spike at a certain time. We want to change the time at which it spikes, okay? And if we use, something similar to what I did up to this point, okay, so that it has a natural period, we want it to change to a new period. Here's the sort of formulation we do. Okay, so we're minimizing the amount of energy input in, and we solve an Euler-Lagrange equation. Here, theta equals 0 corresponds to where it's firing. I parameterize it so when you reach 2 pi, it fires again. So this is basically just saying I want it to fire again at time t1. Well, if I want it to fire at 0.8, its natural period, and I apply optimal control theory to this, it turns out it fails completely. Okay, it makes the heart cell approach a fixed point, and that's bad. Okay, in the cardiac world, fixed point corresponds to death. Okay, now this is a single cell, so probably this wouldn't kill the poor little rabbit, but anyway, it didn't work. So, and we realized when you do phase reduction, if you remember, I said this function z is evaluating the gradient on the periodic orbit. If my input takes me far away from the periodic orbit, that approximation breaks down, okay? So when we realized that, we said, oh, well, in addition to the phase, we need to take into account kind of the amplitude direction as well. And so going back a while, so with Alex and Igor in 2013, we worked on what we called isostables. I think Igor came up with the name. And here, back then, we were interested in isostables for a stable fixed point. And so the thinking was, can we generalize the notion of phase from a stable periodic orbit to what would that mean for a stable fixed point? And so I'll show the movies here to illustrate. So there's a stable fixed point down here. In this case, it's globally stable. So every initial condition approaches that fixed point. But if you start with initial conditions on the same isostable, you see how they approach each other in phase with each other. Okay. Now everything goes to the fixed point, but as you might imagine, if they're out of phase with each other, it's kind of like, well, they don't kind of approach always crossing the same isochron. This is when you have real eigenvalues. When you have complex eigenvalues, this is the sort of picture that you get. Okay. And so then a few years later, with my student Dan Wilson, we generalized this notion of isostables to periodic orbits. And basically, the idea is you choose coordinates such that this, what I call isostable variable, psi I dot, has very simple dynamics here. Okay, so the surfaces of constant psi I are called isostables. Okay, and here, here the periodic orbit is just a circle. I made some non-trivial kind of azimuthal dynamics just to make it slightly more interesting. But in this case, the isostables are just circles. Okay, but you can think of it as if I start with this circle, evolve a certain amount of time, I end up on that circle, and I evolve longer, I end up on the next circle. Okay. Okay, they're related to Koopman. In fact, I think that was the insight that came from Alex and Igor that this is fundamentally a Koopman idea here. Okay, so what we did was, we called it, I don't like the name, but we called it an augmented phase reduction, where we do the phase reduction as before, but we also have this additional equation for the isostable variables. And then if you consider just the least stable direction, here I have n-1 isostable variables. But if we consider the least stable direction, you can say, oh, well, we can approximate it as just a 2D system like this. Okay. And it turns out, okay, in that reduction, you get what we called isostable response curves. I think Hiroya called them amplitude response curves. They have their own adjoint equation that you can solve. Can do it analytically in certain cases or numerically. Okay, well, so then for our timing control problem, which failed when we tried to apply just kind of the standard phase reduction, what we did was we added this additional term here. So psi equals 0 corresponds to being on the periodic orbit. And so basically what we're doing is we're designing an input u, which minimizes the amount of energy needed, but also keeps you close to the periodic orbit. Okay, why is that nice? Well, that's where our approximation is good, right? If we're near the periodic orbit, then the phase response curve is a good approximation of dynamics. Okay, and so then when we did that, so this is what I showed you before, when we didn't include this additional term, it fails miserably. Whereas when we do include it, you can't see it very well, but the black curve is under control. And then when we turn it off, we're on the nice periodic orbit that we wanted to be on. Okay, so we're able to shift things in phase very nicely. I should say, I mean, we toyed around a little bit with this as an idea for how to treat jet lag. Okay, when you travel, your circadian rhythm gets out of phase with what it should be. You just want to shift the phase. Okay? How do you do that? Well, do an input. Okay. At any rate, as I say, what's my for talking about this? Most of these ideas, not all of them, but most of these ideas were developed independent of Koopman theory. And, so if you talk to Winfrey, if you talk to Guckenheimer, Bart Ehrmantraut, some of the big names who are associated with this style of work, they never thought Koopman, okay? Now, Koopman is clearly related. So, many of these ideas were developed independent of Koopman, but they're certainly related to Koopman. But I hope I convinced you that phase reduction is a powerful approach for formulating and solving interesting control problems. And the interesting observation is what matters for control is really the gradient of the isochron and the isostable field, not so much. So typically when we do phase reduction, we don't actually need to calculate the isochrons themselves. We just find the phase response curve, which comes from it's the gradient evaluated on the periodic orbit. The last thing I want to mention is, so in 2019 with some of my students, we called it a tutorial article on phase reduction and phase-space optimal control for biological systems. So it talks about, a lot of these things. And then later with my student Dan, we wrote a review article on controlling populations of neurons. So I just showed you one idea we had on this optimal chaotic desynchronization. I'd say we had at least two other major ideas for how to control them. And then, of course, there's other researchers who have been developing their own thoughts about how to do that. But at any rate, with that, I think I'm done. So thank you.